This is DBL Sprint 1 Group 8 presentation. The speaker is specified on the slides. We start with context and understanding. Our group interprets the assignment as developing an automated CNN-based system to classify chest X-rays into 5 thoracic disorders or determine the absence of disease as displayed above. Chest X-ray analysis is challenging due to noise, label uncertainty, and overlapping visual symptoms. To address this, we propose a hierarchical structure, first distinguishing healthy from disease states, then identifying specific disorders. Our research focuses on technical performance, evaluated using the F2 score, and ethical implications, particularly how varying rates of false positives and false negatives affect clinical decision making and patient outcomes. In our multi-class scenario, type 1 errors represent incorrectly identifying a specific disease, while type 2 errors occur when the model misses the disease altogether. Our aim extends beyond performance, emphasizing responsible and ethical clinical deployment. We identified stakeholders by considering who would be directly affected by the automated system. Specifically, we selected radiologists who rely on the system to assist clinical decisions and patients who directly experience the outcomes of these decisions. Radiologists rely on diagnostic tools for accurate and efficient clinical decision making. Thus, the reliability and accuracy of our system significantly influence their daily practices and professional responsibilities. Patients directly experience the consequences of these diagnostic decisions, facing potential impacts on their emotional well being, healthcare treatment paths, and overall health outcomes. By centering our efforts on these stakeholders, we aim to address their needs responsibly and ethically.
The research question that will guide our work is to what extent does modifying the structure of CNN-based chest X-ray classification system impact both model performance and ethical considerations in clinical deployment. To break this further down, we explore a technical sub-question relating to classification system F2 score across 5 theoretic disorders, and ethical sub-questions relating to type 1 and type 2 errors stemming from the changes done to the CNN. Since reducing false negatives is more critical in medical classification than reducing false positives, we chose F2 score as our primary evaluation method. To allow for a multi-class error rate, we are using one versus rest approach by assessing each individual disease against another. Our research has a direct relevance to key stakeholder groups: diagnosticians, for whom we provide a computer-aided diagnosis tool that can be combined with human expertise, and patients, for whom a better model performance leads to fewer misdiagnoses. Both of the groups are also interested in reducing false negatives, as those could delay treatment and worsen health outcomes, and reduce false positives, maintaining trust in AI-assisted diagnosis, and reducing unnecessary stress and additional costs. Building on our research goals and our stakeholders, we can explore technical aspects such as improving model performance assessed by F2 scores and via semi-classification analysis to understand and account for common model weaknesses. Moreover, we can explore technical aspects such as error rate analysis, examining how differences in type 1 and type 2 errors vary between the original and modified models, and understand how those misclassifications between various diseases vary across them. Moreover, automation bias explore potential over-reliance on AI by radiologists in the clinical settings.
Our dataset consists of 25,000 grayscale chest X-ray images split up into training and testing images, with the latter being twice as big. It includes 6 classes, representing 5 medical conditions, plus a no-finding category. In the graphs, we can see the class distribution in training and testing data. This dataset will help us train models for chest X-ray diagnosis. We apply specific strategies like normalization, augmentation, and balanced batching to address class imbalance. We also focus on evaluation metrics using F2 score, precision, and recall to ensure fair model assessment. Next, we highlight the real-world impact, as accurate predictions can be life-saving. We test robustness to noise, ensuring the model handles real-world variations, and finally, we address ethical consideration, including patient privacy and data security.
The workflow of the code begins with loading and normalizing image data into PyTorch tensors, which are multi-dimensional arrays that efficiently store numerical data. The neural network starts by learning with processing images through several layers. Convolutional layers apply small filters that are called kernels that slide across the image that detect features like edges and textures. These feature maps then pass through pooling layers, which reduce the data size by focusing on the most important information. Fully connected layers use the extracted features to make predictions, and nonlinear activation function called ReLO enables the model to capture complex patterns in the data, while dropout layers help prevent overfitting during training. Then backpropagation refines the network's weights by computing the error between predictions and true labels, calculating gradients. To address the dataset's inherent class imbalance, a custom batch sampler generates balanced batches, ensuring no bias toward over-represented classes. The training process employs a stochastic gradient descent with momentum, which optimizes the model's weights by reducing classification error over multiple iterations, called epochs. The model's performance is then evaluated using a separate test dataset where predictions are compared with actual labels to calculate the loss using a cross-entropy loss function. Training and testing losses are tracked over epochs to measure the learning progress. Finally, the trained model and its performance plots are saved and visualized using Plottext. For improvement ideas, we will initially test out a few color parametric changes like playing with the saturation and contrast of black and white in the given X-ray images. Then implementing a hierarchical structure like UNet, which is very precise for spatial recognition, in our case medical images, would be nice and efficient. Adding an encoder and decoder function would give deeper feature extraction and better understanding of both global and context and local details. And lastly, moving from a multi-level to a binary classification into each layer in the UNet structure would account for a more confident classification for each layer.
To model our performance, we looked into accuracy, specificity, precision, recall, and reliability. And we decided to go with the F2 score in order to emphasize recall or precision when looking into the ethical aspects of um, type 1 versus type 2 errors. We looked at the ethical aspects of false negatives, false positives, and the bias that might be influenced on radiologists, namely what the most severe medical consequences of false negatives for each disease in our data set would be, what psychological and financial building burdens do false positives create for patients, and how can we ensure that AI does not reinforce existing biases in radiologists. We took this into account when making our main ethical question: would prioritizing recall, namely F2 score and the measurement, be ethically justified even if it increases false positives?
In the upcoming weeks, we'll be occupying ourselves with the following tasks. During structured research, we'll be browsing for literature about possible structures in a neural network and choosing those which seem promising and feasible. We will be training our model using the structures we found. We will look for more literature about hierarchical models specifically as they look promising, and then taking a look at the results, we will try to interpret them and calculate F2 scores so that we can compare different models. We plan to tackle upcoming technical challenges by combining knowledge from our prior courses, looking for resources and literature online, and playing around with the code to implement different model structures. We'll use heat maps to check for similarities between classes so that we can take them into account while developing our model. We will keep checking the running time of our codes to make sure it won't take too long to run. Lastly, we will look into techniques to handle class imbalance, such as the synthetic minority oversampling technique.
The task planning outlines what our plan is over the next sprint, focusing on model refinement and ethical evaluation. We will begin with implementing some further image processing, including contrast normalization. Simultaneously, we'll research different model structures, including the possibilities of integrating a hierarchical structure and binary classifiers into our current model. Next, we'll implement and test different model configurations by varying the number of epochs, batch sizes, and model complexity. Each variation will be evaluated based on computational complexity and F2 score metrics, which allows us to make an informed decision about which structures to use in our model. Having decided on a model, we will be able to conduct an in-depth analysis regarding the ethical question, focusing on differences in performance across the disease classes. This will give us insight into what final adjustments we need to make to minimize the respective ethical risks. In the final phase, we'll perform a quantitative and qualitative performance evaluation and document the final model specifications along with ethical considerations. Thank you for your attention. Here are the key resources that guided our decisions in this presentation.